Okay, I think it's recording now. It should. Okay, so today I will show you how to simulate rigid bodies with contacts and collisions, and also stacking. Last lecture we covered equality constraints for articulated rigid bodies that were of the form C of, and then there goes the location of the two connected bodies. R2, and it can also depend on time in general, equals 0. That was the basic formulation. And now contacts are a little bit more involved because, contacts are kind of one-sided constraints. They are also called unilateral because they are usually defined by an inequality. This. So that's why sometimes these inequality constraints are called unilateral constraints, while the equality constraints are called bilateral, kind of two-sided. But that's not all there is to contacts. So this only says that there should be no penetration, meaning, what it says. But also, bodies should always only push apart, but never pull together. So also the forces kind of need to be bigger than 0. And also, there's a third component, and that is when either the force or this distance between the two bodies is equal to 0, then, well, at least one of the two always needs to be 0, meaning that this can be denoted by just the product of the two. This needs to be 0, and this holds for all the contacts. So this formulation is called Complementarity Conditions. And it basically means that when there's no force acting between the bodies, then the distance between the bodies should be greater than 0. Or if the distance is 0, meaning the bodies touch, then the force needs to be greater or equal to than 0. Okay, so there are a lot of formulations that are equivalent to this. So for example, there is, let me just show you one example for this. One can also say that the minimum of the force and this constraint violation should be equal to 0. One can easily figure out that this is equivalent. So let's make a little table. I'll go through all the cases. So suppose when C is smaller than 0, equal to 0, or larger than 0. Okay, what's then with the minimum of the two? Well, if both are smaller than 0, then also the minimum is smaller than 0. Well, I shouldn't have put an equal sign here, obviously. Okay. Okay, so, and if one of the two is smaller than 0, also the minimum is smaller than 0. Now, if both are greater than 0, then also the minimum is greater than 0. And if one of the two at least is equal than 0, then the minimum is 0. So this shows that this is equivalent. And there are even a number of further formulations, and just stick. So maybe I can refer to a paper or document that covers this. Well, for some reason it won't open my USB stick. Well, anyway, so the document I mean is from Kenny Erleben. It's called Numerical Methods for Complementarity Problems, I think. Well, you can just Google Kenny Erleben Numerical Methods and you will find it. Complementarity problems. Okay, so in general, one has to distinguish between two different kinds of contacts. So there are collisions and contacts. With collisions, we mean basically the first point in time two bodies are touching, so impacts basically. That also includes bouncy collisions. And then there are contacts, which refers to resting or sliding contacts with a prolonged touching. So the classic approach is the penalty method. And there you usually figure out which points are intersecting, and then you kind of construct springs to push the bodies apart again. And this method is still used in engineering or simulations where it needs to be really accurate. But there are a number of drawbacks of this method. So it is usually very difficult to choose the spring constants, especially if you have multiple contact scenarios. And also you usually need a very small time step, what makes them quite inefficient. For some time, around 2000, it was also popular to use impulses for bouncy collisions, or collisions in general, and penalty forces for contacts. But actually now, in the computer graphics community, just choosing impulses for both contact and collisions has prevailed. So the approach we will cover here is a still very popular solution, the pairwise propagation. And the paper I will introduce here, or the technique, was presented by Gündelmann et al. In 2003, so it's already more than 10 years old, but still this technique is the basis for also many modern techniques. 3, and it's called non-convex rigid bodies with stacking. Okay, so how does this work? The algorithm. So this is the basic pairwise propagation method, and it's quite similar to the method we already used for the last lecture for the equality constraints. So again, we start by initializing all the positions, and then we loop through all the time steps. And first we apply the external forces and torques to the bodies, and then we do this these solver iterations again to project the constraints. And now, of course, we need some form of collision detection, because contacts, well, this is a rather separate geometric problem that just looks at a certain configuration and figures out which pairs of body are colliding or intersecting. So I will come to how to implement such a collision detection for some simple primitives in the end. But for now, let's just say that we, from this collision detection, we get a number of body pairs that are intersecting, and it also gives out which, it returns the contact normal, so the direction in which bodies should push each other apart. So these are the normals of the ith contacts, and also the positions where these contacts occur. So let's call it AI, BI. Okay, so and then so this collision detection is invoked after we update all these ones. So so the contacting bodies intersect, and then we go through all the contacts and resolve them. So that's pretty much the same we did last time. So we do these previews for the two associated bodies of the current contact, and then we resolve this contact. This is a little bit different, but I already last time showed you this constraint, this plane constraint. Let me show you. That was this one. And now we compute first the relative velocity at these contacts, so how quickly the two pairs are approaching. And that's what we want to set to 0 for inelastic collisions, or for elastic collisions we want to set this to minus u rel. Okay, here we have to check again if the bodies are really approaching, otherwise we don't need to resolve this collision. And then we compute this impulse. Just the pH is the one-dimensional impulse, and this part is basically the same we already had last time, except for that we use the relative velocity here instead of the penetration divided by the step size, meaning that we only want to change the relative velocity to 0 or minus 0, to 0 or minus u rel. And this epsilon now is the so-called coefficient of restitution, which defines the bounciness of the collision. So there's so an inelastic collision has epsilon equals 0, and an elastic collision has epsilon equals 1. And of course, we can also have 0.5 or something in between. That's not quite in focus, is it? Oh, no, it is. Okay. Then we can project this this impulse back to 3D and apply it as we did last time. So so maybe let's have a look at this formula and in a little bit more detail. Okay, so what we want is we want the velocity after the application of impulses to change, right? So let's call this maybe urel plus. And we only want to change the normal component of this velocity to minus epsilon times urel. This is the relative velocity at the contact before. And so this can be done this. And urel n is just the relative velocity times the normal of the contact. Okay, and putting this together we get minus epsilon urel n equals n plus this p dash. So we get p dash equals minus 1 plus epsilon transposed All right, so now what's with why do we need to do the collision detection in every solver iteration again? Well, the reason is if you think, for example, about Newton's cradle, you know, like this kind of pendulum with several spheres. We've certainly seen this before. And now if we want to resolve a collision of one sphere, you know that in the end the last sphere should separate, right? And this can all happen in one time step, all these collisions. And so in this case, we in each solver iteration, we only resolve one collision. So that's why we need to do this collision detection again each time. And this lets us simulate such a mechanism. Okay. By the way, there are also other more accurate collision detections that don't just look at one point in time if bodies are intersecting, but it also accounts for the position of rich bodies and can determine the point in time the collision happens. And some methods try to actually resolve these in a chronological order. But for interactive simulations, as for example in games, this is not very efficient, because in many scenarios you have the more bodies are contacting, the slower it gets, and it can actually, like for some stacking scenarios, it can actually get extremely slow. So that's why we want to detect all the collisions just in one go. Okay, and so what happens if we have a body with infinite mass? Does that make sense? Well, kind of does. Because when the environment is usually seen as a body with infinite mass, because it never moves, and also the inertia is kind of set to infinite. Now, of course, numerically, infinite is not a good number to deal with in computer science. But if you look at all these formulas, actually we usually have the inverse inertia and also the inverse mass, also in these formulas. So it might be better to actually save the inverse mass and the inverse inertia instead of the mass and the inertia. Okay. Now, so right now, when we resolve the collision like that, we don't have any friction yet, right? So the bodies will just slide off, basically. So how do we deal with friction? I think the most popular model for friction is the Coulomb friction model, also called dry friction. And so what this does is basically it simulates the effect that when you have a rigid body and you give just a little push, it will not move usually. So that's called static friction, where the body's kind of sticking. But at some threshold, when the push is strong enough, it will start sliding. And that's called kinetic friction. Because still there's an opposing force or resistance. Okay, so what do we need to change to simulate friction? Okay, so first we assume static friction. For that, let's first look at, so we already had the normal velocity. And the tangential velocity is the other component, which is just the relative velocity minus normal velocity times the normal. So this is the jth contact normal. And now the velocity we want to have after the application of the impulse is minus epsilon n times the normal, right? So we don't want any tangential component for the static friction because it's sticking. And here again, the formula for applying an impulse. Right, and resolving this to P. Alright, but so this is if we always have static friction, this would be how to compute this. But now the Coulomb friction model goes as follows. So depending the larger the normal force or the normal impulse, so the heavier the body basically, the larger the push needs to be to move it at all. So to switch to kinetic friction. Epsilon is this coefficient of restitution. So it's like 0 for inelastic collisions and 1 for totally elastic collisions. So what we have to test is if this impulse is outside the so-called friction cone. So let me make a little drawing. So suppose this is our contact with the contact normal, and we have some impulse P for static friction. Then we need to look at the tangential component of P and check whether it's inside the friction cone. And this is just some simple geometry. Now here, this is the static friction coefficient, which basically determines the slope of this cone. So the larger it is, the more sticky the contact will be. So actually the slope of this cone is 1 over nu. Right. And then we need kinetic friction. Okay, so the kinetic friction is, well, similar to the usual normal friction, but in addition we want to oppose the tangential component of the relative velocity of the contact. Well, epsilon is this coefficient, the bounciness basically, and nu is the friction coefficient.
Okay.
So the bigger nu, the more sticky the friction will be. Right. And then okay, so let's look at the kinetic friction. For that, let's introduce first the vector t, which is just the direction of the tangential component of the relative velocity. So minus t is basically the direction in which the resistance, the resistant force needs to be. So basically, in addition to this normal component, we have a tangential component. Like that. So now this nu is the kinetic friction coefficient, and in general one chooses the same as for the static friction coefficient, but one could also use a separate one, meaning that it takes a lot of force to set the body in motion at all, to overcome this stickiness, but then the resistance will be rather low. That would be an option, but then it should be smaller than the static friction coefficient. Okay, but you can also just use the same usually. This gives already quite good results. Forgot this one. Okay, so now how do we compute this P dash? Well, so again, you can prescribe relative velocity after the application of impulses. Times p. Now let's take the dot product with the norm, just for the derivation. Oh, this is not a vector. Equals.
Sorry, I don't quite understand what you wrote above there. It's divided by dot n.
Oh, well, no, I just want to denote that on both sides we make the dot product. So, I don't know, in Germany we usually do it like this, so just forget about this part. This is just equivalent. We just take the dot product with nj. Yeah, maybe this is a little bit confusing. So as the new the relative velocity after this. We want to have the normal component is supposed to be minus epsilon url n again. So we still want to have that boundness in the normal component. And then for P, we can just plug in this formula. P dash. Now resolving this to P dash gives us minus 1 plus epsilon times url n over okay, and then we get the real impulse, the 3D impulse, just with this formula again. And yeah, then we can apply it. Right, so yeah, this is how to simulate friction, this method. Okay, but still with this general approach, there are two major problems I want to come to now. So the first one is that if we have a, well, for that let's consider a very simple example. Okay, suppose we just have one rigid body, rectangle like this, which is sliding down an inclined plane, and it's also bouncy. So let's suppose it's very bouncy. Now what this algorithm does is first we apply gravity to the body, meaning this will be changed from tangential to point slightly down into the plane. So in this first, in these previews, it will be inside. So we detect the collision, and when we resolve the contact, we take this velocity and now since we have a restitution of 1, it will basically just be reflected and point slightly upwards, meaning that actually this body will just start to bounce, although actually it should just slide down the plane. So a number of solutions to this problem have been suggested in the literature. So there's many people, for example, just use a threshold to kind of distinguish between collisions and contacts. So based on the gravity, you can think of some threshold, but that's not a very accurate way of dealing with this, obviously, and not very nice because it's got this weird threshold. So in this paper that I referred to from Gündelmann, they came up with a better solution to this problem. And so what they do is the following. They first make sure that they only handle collisions. So for example, if we have, let's look 2 cases. So here clearly this body is supposed to collide with the ground, and this body is just sliding. So at the beginning of the step, the velocity is tangential to the plane. Now what he does is he first looks at only collisions by using the old velocities without updating them first, so that the collision detection will not notice sliding or resting bodies, just the ones who truly are impacting. And then in a later step, he will treat all the contacts using new updated velocities with the gravities. So this is a quite elegant way to deal with this. Okay, and a second problem with this method concerns this contact resolution. So in the case of multiple contacts, there is the problem that when you think of 2 or a number of boxes resting on each other, now if the contacts we detect are given like maybe from top to bottom, and we would try to resolve them in this order, we would run into problems because for this first preview, the bodies all fall down a little bit into the ground, but only the lowest body will actually be in the ground. So resolving these top collisions will not do anything with the simulation. And we need very many iterations until this top body even notices that there is a ground. So it would be much better to go bottom up instead of top down with this resolution. But even then, the convergence can be quite slow. So if we look at only 2 bodies, so first what happens is they both fall into the ground a little bit. Then we resolve this first collision, which means the lower body will be pushed into the top body, basically. And then, even worse, when we now resolve this collision, or contact, then the top body will be pushed a little bit to the top, but the bottom body will also be pushed into the ground again. And you can probably imagine that it gets worse for larger stacks and also for large mass ratios. So if the top body is very heavy, then this will take very many iterations until both bodies are not penetrating. Yeah, let's look at a method that can deal with that handles both of these problems. Okay, and just for clarification, this part of the algorithm, just going through all the contacts once, is also called sweep. So I abbreviated this here. Okay, so what's different now? Well, this part is basically the same. This is what we had so far to resolve all the collisions, except that we now use the old velocities. So here for this update of the external forces and torques, we introduce V and omega dash. So we have both available, both the old and new velocities. And then for this preview and the collision detection, we use the new velocities. But for the resolution of these contacts, we use the old velocities. And this is quite important because in both the collision phase and the contact phase, we need to use the same velocities for the update. So in this case, the new updated velocities, because otherwise it might happen that in this contact phase we notice some contact that hasn't been registered in the collision phase. So we basically accidentally would ignore some bounces for a collision. So it's very important to do the same for both phases in the collision detection. So only for the resolution, for the sweep, we use the old velocities here. And then in this contact phase, we use the new velocities. So here again, I update all the velocities with the forces, and from this point on, we don't need the old velocities, so I can just use V and omega as the velocities. And then we iterate a few times through all the contacts, and for these we set all the bounciness coefficients to 0, because we already handled the elastic bouncy collisions, and in the contact phase we don't care for bounciness, so basically we set epsilon to 0 for all the collisions. Okay. Now with this collision detection here, that is changed a little bit. So now what we wanted to find is like the order of how to resolve these contacts. So for stacks we want the bottom up order. And this can be done by, well, of course, the most trivial approach would just be to sort them just by the y coordinate. But a better and more general way is to individually update each body, check what body is colliding with. So these will usually, for some stacks, be the ones below it that it's resting on. And then we set it back, so this is just a temporary one. And then we do this for every body, and thereby we can construct a sort of graph that connects all the bodies from the ground up. And then we also assign each body a layer. So, for example, in layer 1, there will be only the bodies resting on the ground, and in layer 2 there will be all the bodies resting on layer 1, and so on. And then in this contact resolution phase, I don't know what's wrong with the focus. Yeah. I think there was some way to do it. Anyway, okay, so now we do a few sweeps through all the contacts in a bottom-up way, but still for very high stacks, as I mentioned before, we can still not expect this to resolve all the penetrations in a reasonable number of iterations. So what the paper from 2003 again meant as a method of shock propagation. And that works the following way. So if we have some stack, we first only look at the first layer and resolve all contacts within this layer resting on the ground. Then we basically fix the bodies of this layer, of layer 1, and then resolve the second layer, so that the bottom parts will not be pushed into the ground again. So this is a kind of hack to get all the to push all the bodies out of each other, and we only need to go through all the layers once, fixing the layer below the current layer, resolving all the collisions, and of course unfixing the bodies. So basically setting their masses and inertia tensors to infinity. And yeah, this works actually quite well and is also efficient. And yeah, that's the whole algorithm. And in the end, we just need to update all the bodies once, the locations of the bodies. Right, so this is basically the whole algorithm. Now, so let me maybe shortly talk about the equality constraints we handled last time. So are there similar problems for articulated bodies? Well, yeah, of course. I mean, since the method is pretty similar, also the order of resolving all the joints matters. And this can be quite a big problem for convergence. Also, large mass ratios can be a problem with the method I introduced last lecture. But there is a way around it. Now, this will not be part of the homework, but let me maybe anyway mention how this can be dealt with. So this was the method we had in the last lecture. And now, instead of resolving all these joints one by one, there is a way to resolve them globally, meaning that you can basically put all the update all these bodies at once, and then measure all the constraint violations at the same time for this new state, and put them in one big vector D that contains all these constraint violations. And then also one needs to construct a global matrix that accounts for all these joints at the same time. Now, I won't go too much into detail about how to construct this global matrix, but it's a sparse symmetric matrix which can be solved with Cholesky factorization, and doing this will only require few iterations and also be not as sensitive to large mass ratios, and also the order of constraints doesn't really matter. So there are ways around this, but these methods have other drawbacks again. So last lecture we came across some redundant constraints, for example. And while this iterative method has no problems with redundant constraints whatsoever, when putting this into a global equation system, this will actually lead to a singular matrix. It needs to be dealt with in some way. So there are other drawbacks and also some solutions to these. But maybe for now, let's get back to the contact formulation. So I wanted to show you how to resolve collisions. So let's talk a little bit about collision detection. So I think probably the easiest collision detection is if we only have spheres. So let's suppose we only have spheres. Well, I mean, this is maybe too small. So this is one sphere with a position x1 and a radius R1. And the second sphere. So what we need is, first we need to check whether they are intersecting or not. And then if they do, we need a contact normal and the location where they intersect. So basically they are intersecting if, well, I mean, just if this distance is larger than the sum of the two radii. This is quite simple geometry. This is smaller than R1 plus R2. And if they do intersect, so let's maybe then the normal will of course be well, just this direction normalized, right? So it's just x2 minus x1 normalized. And these points are also quite easy to determine. So let's call this point B, and that is on the surface of the second sphere, and this point A. Then A is just x1 plus R1 times the normal. And B, undoubtedly, is just x2 minus R2 times the normal. Okay, so spheres are pretty simple, but also like the dynamics of spheres is not that interesting. I mean, you can hardly notice if they are rotating or not. So let's have a look at at 3D boxes. So how can we check for interference boxes? Okay, for that, let's just. So this is one box. This is another box. Now the centers of gravity are x1 and x2 again. And then let's let's denote these the dimensions of these boxes with so dimensions. Let's denote them with HB X, HB. So so for the first body, HAX, Y or Z. And for the second body, HB, X, Y, Z. So what else we need? Well, obviously the orientations of these boxes. Okay, so there's a quite intuitive theorem called the separating axis theorem, and it basically states that if you have two convex bodies and they are not intersecting, then there must be some plane between the two bodies that doesn't touch the bodies. I mean, this is quite intuitive, obviously. So in this case, this would, for example, be this plane. And so this is called separating plane. And the line orthogonal to it is called the separating axis. And what one can do is just check for different separating axes and then basically project these bodies onto this separating axis. So here we will have the vector t, which is just x2 minus x1. And then we look at projection onto the separating axes of these boxes. So this is the one for the first box. For the second box will be this one. So we only look at half the projection. And if we find any separating axis where these two line segments don't intersect, then we know that the bodies will not intersect. So, I mean, how many axes do we need to check for this? Well, in 2D it's pretty simple. We just need to check 4 different axes, and it's the one parallel to the edges of both boxes. And if none of these if none of these line segments are separate, then we know that they intersect. So in the 3D case, you might think that we only need to check 6 axes then, so the parallels to the edges of the boxes. But actually we also need to check their cross products as well. You can easily check this by thinking of 2 boxes that are kind of close to each other, well, at some edge for both. Then none of these other 6 axes will work. So we need to check these 6 axes, then another 9 axes, because like 3 times 3 cross products. And so this is just So yeah, let me maybe make a little example. So let's call the direction to check. Let's call that S. And now the vector t. Let's transform the vector t so that at least one of the two boxes, or the first box, is aligned with the coordinate axes, because that simplifies the computation somewhat. This can be done by R1 transpose times x2 minus x1. And then we have to check the separating axes. Well, let's call it AX. So then these become pretty simple because we transformed it into the local coordinate system of the first box. AY. And AZ, well, it's pretty simple. And then the coordinate, the axes of the second box. They are just the columns. Oh, sorry. So from the second box, we take the columns of R1 transposed times R2. So this is basically the orientation of the second box as seen from the local coordinate system of the first one. Well, and then of course we need all the cross products. Cij equals AX cross, well, AI cross BJ. For I and j, x, y, or z. And so looking, for example, at the separating axis AX, we have to check whether t times, or in general, t times s. So this is basically this distance. If this distance is bigger than dA plus dB, so that's what these distances are. And now for so how to compute dA and dB? Well, dA is just the sum equals x, y, or z. The dimensions of the box times times A. And accordingly for dB okay, and of course, like a lot of these formulas can be simplified because the A, X, Y, and Z have just one component non-zero, and yeah, so this is how to check whether two bosses are intersecting. But of course, we would also like to have some contact normal and some contact point. And this is a little bit more tricky. Now, there are methods that just go through all the cases and try to find it this way, but this is actually really cumbersome. So let me show you maybe a slightly more general method that also works for quite general bodies. And that is that works with so-called signed distance functions. I don't know, did you have signed distance functions yet? So this is basically an implicit way of describing the surface of a body. So, for example, for a sphere, this would be, so let's suppose we have a sphere with a radius r that is just, its center is just at the origin, and we want to evaluate this signed distance function for some point. Then this would just be p minus r, meaning that when we are at the surface of the sphere, this is 0. If we are inside the sphere, this is negative and denotes the distance to the surface. And if we are outside the sphere, it's positive, giving the distance to the sphere. So for example, so for a rectangle, if we visualize this signed distance function, it would look something like this. So here this function is, this is the signed distance function for a rectangle. So it's 0 here at the edges of the rectangle, and in the inside it denotes the negative distance to the surface, and outside the positive one. So now what's the formula for the rectangle? Well, there's one quite neat way to do it. Okay, for that let's define a vector m, which is px, py, pz. These are the dimensions of the box. And then this function is just the minimum of the maximum of mx, my, mz, 0, plus the norm of So this is a simple way of basically avoiding all these case distinctions using these min and max functions. But of course, you could also just manually try to figure out which region am I in, and then either just use the distance to this point, or the distance to a plane or right. So what can we do with the sign distance function? How do we compute? How do we get the place where the collision occurs? Well, if we have two boxes, we could, for example, just check the corners of the boxes, whether they are inside the other box easily. And usually you do this both ways around. So we check the vertices of box 1 for the sign distance function of box 2 and vice versa. But there are cases where this is not enough. So if you think, for example, of two longish boxes that kind of intersect at their edges, then neither vertices will be inside the other box, right? So this is why one simple way around this is to just sample the surface of the boxes and then check all these vertices on the sign distance function. Yeah. So what's the time? I think we are in time. Okay, so